Hi, thank you for joining our presentation on the CapBank Power Factor Correction System, including team members John Ruehl, Tyler Adkins, and Peter Ranley.
Here's our agenda for today. Our first is our objectives and personal background. Then we'll go through power factor and how to correct it, examine the scenario we used in our model, the solution in detail, and then analyze the simulation data collected. We'll then go through a cost-benefit analysis, then our schedule with a Gantt chart, and then we will go through our conclusion and references. The goal of this project is to correct power factor by using a capacitor bank. Power factor is the ratio of real power to apparent power, and this is a measure of efficiency of power delivery. Power factor can be lagging, which is inductive. It could be at unity, which is purely resistive, or it can be leading, which is capacitive. A cap bank, on the other hand, is a collection of capacitors in series, parallel, or both with the load. Capacitor banks help by making the power factor better by counteracting the inductive loads, such as an electric motor. There are a lot of benefits to having good power factor. The two main are having a cheaper electric bill, as most electric companies charge by apparent power. The second benefit is that the capacity of electrical equipment is greatly increased. We had two main objectives for our project. The first is to model a realistic electrical system that needs power factor correction. Honda transmission plant provided us data from one of their substations so that we could use it for our model. In figure 1, you can see the power factor for the month of March this year. You can see that the mean is roughly 75% power factor, the max about 84%, and 60% being the minimum. So by all means, this is not great power factor, as it is always below 85%. Our second objective is to analyze the cost benefits and the negatives of providing a capacitor bank solution and see whether it is worth implementing into a system.
All three participants of this project are EE students looking to work in the electrical power industry. We also have a minor in electrical energy and smart grid. I am John Ruehl. I've rotated my last 4 co-op terms with Duke Energy Renewables. I have experience in generation, and starting June 1st, I will be working as a full-time engineer at Duke Energy.
Hi, I'm Tyler Adkins. I worked 5 co-op terms at AES Ohio, previously known as Dayton Power and Light. Varying responsibilities and departments. I've worked in test department, which is a lot of wiring relays and logic there, electric meter, substation engineering, which involves a lot of wire diagrams, schematics, writing those up, giving those to the guys, and finally AC network, a lot of downtown network, cables. A lot of that was a lot of time supervisory roles or developing things and programming things for guys to use in the field. But now I'm a full-time CDO supervisor, and yeah.
All right, and I am Peter Ranley. I did all my co-op terms at Honda Transmission Plant at Russells Point, Ohio. I did 3 co-op terms in facilities where we focused on distributing electric, water, and stuff like that. And then I had 2 co-op terms in 4-wheel drive, which is production department. I'll be starting my full-time here in June at the stamping department at the East Liberty Honda plant.
So introduction. So what is power factor? It represents efficiency. So you don't want machines working against themselves, wear and tear, heating issues. It shortens their lifespan. Faster things wear out, faster you've got to replace them, right? So this also, if things run efficiently, it reduces your electric bills. Lower power consumption equals lower bills, right? So the less these machines need power to run efficiently, the better. And then look at it environmentally. from an environmental aspect, efficient, motors give off less pollution, less gas emissions, meaning burning less fossil fuels. I really enjoy the beer analogy. I think it's really helpful. So if we're looking over here at this mug of beer, you've got apparent power, which is the mug capacity. How much beer can you hold exactly, right? And then that's kVA. Active power is the real power. It's kW. How much beer is actually in it compared to the foam? Right there, we're like, I don't know, 2/3, right? And then reactive power is the unusable power, the kVAR. That's the foam, and that's what we don't want. No one wants to drink a mug full of foam. So obviously, the more beer, the better. We want more beer than foam. But we get power factor by beer divided by capacity, or real power divided by apparent power. Low power factor means, a lot more reactive power, and that means a lot more foam. Power factor correction. So if we've got bad power factor, how exactly are we correct it? Well, the most popular way to do it is capacitors. Utilities and commercial customers do this all the time. A lot of times you'll see utilities put them in substations, and a lot of times you see in figure 3, they'll put them on the poles. Commercial customers will put them on their property to help their motors run more efficiently, better power factor, and helps their bills. But I would say for this scenario, look at peak energy consumption. So let's say every morning, you're someone who works from home and needs their power. Well, at peak energy consumption times, like in the morning when a lot of these factories are turning on their big 3-phase motors, that's a lot of draw on the circuit. And if, let's say, you're on the same circuit as them, you'd be able to see it if there wasn't, the capacitors and other regulating devices helping, kind of level that, that draw, that load. So a lot of times if you'll see flickers or dimming of the lights every time you see these big power peak energy consumption hours. Capacitors allow them to, provide more power, more energy. And so other people in the same circuit won't see these flickers, dimming of lights. They won't see any problems with their services. And it'll also help the factories, the big commercial customers. Their equipment will run more efficiently, and they'll have great power factors.
Scenario. We modeled our system after the Honda substation, like we mentioned prior. This is a 480/277 volt, 3-phase Y, 4-wire substation. Now the neutral is grounded and is not used at all, so it's really just 480 volt, 3-phase. And so the load is 480 volt Y, 3-phase, 3-wire loads. And these are considered variable loads because it is HVAC equipment, air compressors, air dryers, and production equipment. And these all depend on the time of day, time of month, what shift is running, shutdown, whatever. So as you can see in figure 6 for the power data, you can see how much it fluctuates throughout the month of March. And so we had to pick 3 different loads for our simulation. So we went with the minimum, the mean, and the max loads. And we calculated this from the meter data that Honda sent us. And you can see a sample of it in figure 4. But we use the equations in figure 5 in order to calculate the resistance and the inductance. Therefore, we could simulate it in multi-sim. And just to reiterate, there is no power factor correction currently in place on this substation. So for the cap bank design, we had to decide whether we wanted to use a Y or a delta configuration with the capacitors, as you can see in figures 7 and 8. We went with a delta configuration, and the main reason being that the delta configuration receives the full phase-to-phase voltage, which is 480 volts in our case, which gives it a greater reactive power per capacitance. Whereas if you look at Y, you would only get the phase to neutral voltage, in this case 277 volts, so that will give you a reduced reactive power per capacitance. And a delta is typically used for low voltage, and Y is typically used for medium to high voltage. The main negative to a delta is that there's no ground connection, so you need more fault protection in place to protect it. So that you might need current limiting fuses or bushings on both sides of the capacitors. Whereas in a Y configuration, it already has some protection in place due to the neutral being grounded.
So here's our solution or model. Here in figure 9, you can see the capacitors. So right here, we have 4 stages along the right. Stage 1, stage 2, stage 3, and stage 4. So stage 1 is 150 kVAR. Stage is delta load. And then the other 3 are 75 kVAR. Depending on what you need, you can flip them on. So if, let's say, you did stage 1 and 2, that's 225 kVAR. If you need more than that, or just maybe one, just based on the load and what you're looking for, you flip them on. Right now, we've got 3 unique loads. Max load, mean load, and minimum load. So think maybe max loads when all the machines are running about 9 o'clock in the morning. Mean is kind of more like middle of the day, your typical load, what you're going to see, your draw. And then minimum is definitely like, let's say 3 o'clock at night. What are we looking at minimum wise? We got these loads based on the data provided from Honda. They in no way in the real world you're going to have 3 separate loads, but for our testing purposes, this is how we did it with switches. The switches kind of represent in the real world what microcontrollers are going to be operating. So microcontrollers are going to be able to sense and determine what stages need to be turned on and when. We obviously simulate this and try to figure this out. Did not need to program or use microcontrollers. So for simplicity's sake, we just use switches that we used in multisim. On the top left, we've got power factor meters and an oscilloscope. This is how we've gathered data and put it in tables and got waveforms, how we determine the best stages to use for each load. And then obviously the top is the voltage source transformer. Power factor analysis. So this is kind of the data we've gathered via the power factor meters. Power factor based on loads and stages. So if you can see on the left of this table is your kVAR, or the stages you're using. So, and then the top is your minimum load, mean, max. So right now we're kind of shooting for 0.95. That's a very good power factor, and we want that or better. As you can see, there's a no stage, so if we're not applying any power factor to these, so at minimum, we're only getting 0.704, which is pretty bad. But we add 1 stage, like stage 2, which is 75 kVAR. If we applied that, our power factor jumps all the way to 0.975, which is fantastic. And then we got lagging and leading, and I'll show you a little more of that on the next slide, how we determine that. But so right now, but if we applied too much, if we went with stage 1 or maybe stage 2 and 3 that accumulate or added up to 150 kVAR, we can see that now we are leading too much power factor wise, and that's not good. Our power factor is actually getting a lot worse. But as you can see, min, mean, max, we can tell that, we could tell min load that we've got to a certain point where we didn't need to look at any further down at 225, 300, 375 because we knew it was just going to get worse and worse. But as you can see at the mean load, the best power factor is at 225 kVAR, that stage. So that's about stage 1 and stage 2, 150 plus 75. We could also use 300 kVAR, but if we're trying to get the best possible power factor, obviously we want to use 225. And then max, obviously the best we could do is 0.964, and that's with all the stages on 375 kVAR. That's fantastic still, but that's the best we could get unless we added more stages. So reactive power, obviously, once we get to a point where our power factor is dipping under 0.95 and it's leading, we're pushing reactive power back onto the grid. And utilities do not want that. Commercials don't want that. Their power factor is getting worse, and we've got reactive power being pushed back onto the grid. Lagging versus leading. Like I said, lagging is more like when the current is lagging behind the voltage, while current is leading versus the voltage in the other scenarios. So a lot of times it's when there is more kVAR coming from the capacitance, reactive power coming from the capacitors, than there is from the load. That is when leading is occurring. Waveform analysis. So right here we have various loads. Right now, for simplicity's sake, I showed the best 3 for each load. As you can tell back in the last table, our min load, the best power factor was kVAR correction, and it was lagging here. Right here in figure 12 was the max load, 375 kVAR reaction. That is also lagging. And then figure 13, mean load, 225 kVAR correction was the best there as well. So as you can tell, all these look very similar, and that's kind of what we're shooting for. The better the power factor is, the better everything's in unity, everything's in phase. The closer they are to not leading or lagging, the closer power factor is to 1, the better.
Our estimates for cost-benefit analysis are based on the City of Lebanon's bill structure. Based on that, Honda would actually not pay based on kVA. However, they do pay based on kVA for demand. Demand charges are based on the highest peak power consumption at a period of time. In this case, using Honda's model, peak kVA occurred at 592.88 kVA, which we can reduce using our cap bank to 502.63 kVA. Reducing this peak kVA reduces Honda's monthly electric bill by $1,208.44 monthly. We can assume a total cost for the system being around $100,800, and if we finance this over 9 years at a 5% interest rate, we can have this paid back just by using the electric cost savings for the first 9 years, and afterwards the savings would be entirely returning back to Honda. If we assume that Honda had also paid based on kVA, the savings in return on investment would even be sooner.
Here's our schedule for the project in the form of a Gantt chart. The dashed red line is the current date. Proposal, initial design, cost analysis, simulation, and presentation were all of our tasks on our Gantt chart, and they were all on schedule. We met roughly 1 or 2 times a week to finish this project on time.
So our next steps. If this was in a real scenario, our next steps will be we would send out a request for proposal to OEMs to design the system based on our spec. In this case, we had a 150 kVAR step and 3 75 kVAR steps. Afterwards, we would find an electrical contractor that would install the cap bank system and a financing partner. And after install is complete, the OEM would return to commission the unit. What did we actually learn from this project? We learned about the enterprise bill structuring and how commercial and industrial bills or power bills are different than, say, residential. We learned about product design and how using simulation can be used to verify this design. And we also learned about how power factor correction and its effects. So how power factor influences voltage and current of the system and how it does affect power bill costs. In conclusion, our solution has proven that it will improve Honda's power factor for the substation. Our solution will reduce Honda's overall electric bill by over $1,200 a month, with a return on investment of 9 years at a 5% financing rate. If we use this payment plan, this would offset the cost savings for the first 9 years. So Honda would see a net zero benefit for the first 9 years. At this point, then Honda would see a $1,200 a month savings from there on out. Here is our references that we used for our project. And if you have any further questions, you can reach out to our emails below for me, Peter, or Tyler. Thank you for viewing our presentation today.